So the base is U. Maybe
Stop. All right. Let's recompile that. So U is equal to minus kx, and x is obviously theta and omega, so which represents the missile motion state. And the gain matrix is k, determines the correction strength. So if the gain is too small, suppose that 0.1 and 0.005, and suppose the disturbance increases the pitch angle. So the controller will compute U is equal to minus kx, and since k is very small, then U would almost not change at all, which means the correction will be very weak. But you can also have gain too large, because if I were to have 500 and 300, for example, it's going to go for a very large correction. Go up, down, up, down, up, down. So property turned gain. So k is equal to 12 and 4. So controller now computes the balanced correction. So it's a balanced value, not too high, not too low. And so the small gains, the k value will decrease, which is going to create a weak nozzle. So it's going to create a weak correction. And if I have large um, feedback values, then I'm going to have a very large correction. But large correction, what I mean by large correction means large correction doesn't mean, oh, it's going to be very accurate. Large correction means it's going to be very, what do you call? It's going to be too high. It can go too far or it can go too up. Right. So during the hypersonic flight, the dynamic pressure, the Q is equal to half rho v squared. And so since the velocity appears v squared, the small steering commands can produce very large aerodynamic moments. Let's do the programming for it, if that's all right. Can we do a program, like can we do a Python program for this? Can we do a Python program for this? Can we do a Python program? Just for this, we'll do a Python program. Let's do one. Let's do a Python program for this. I just don't care whatever Valentina does. She has way too many people with her. I just don't care. I just don't care, man.